Welcome to this webinar of DHI about integrated urban water management. Before we start, I will introduce myself. My name is Honza Krejcik, and I am acting as a market development director for urban water globally for DHI. And as I mentioned today, we are here to present some of the DHI solutions related to integrated urban water management, and especially the application of digital twins of different urban water systems, whether this is water distribution or collection system or urban drainage or wastewater treatment plant, because all of these subsystems are somehow related to the topic of integrated urban water management. And we will not be focusing very much on the presentation of very deep technical insights of our products and solutions, but more towards their application in different parts of the world, in Europe, Africa, and other parts of the world. So here we are, and we may start with a short introduction how we will be talking to you today within the next an hour or approximately 60 minutes. There will be 3 speakers today. I will do only a short introduction, and a major part of the webinar will be performed by my colleagues from DHI, starting from top, Peter Ingedult, our senior water supply system expert from Czech Republic, Dennis Wanninger, my Swedish colleague, digital system lead in Sweden, and Henrik Sorensen, my colleague from Denmark, the senior engineer on digital lead. And as I was introducing my colleagues, Peter, Dennis, and Henrik, they will each of them talk about different applications and also the different part of the urban water management systems. Peter, as the title shows, he will be talking about application of digital twin in water distribution systems. Then Dennis will follow up by showing applications in urban drainage collection systems, and Henrik will conclude with the presentation of digital twin of wastewater treatment plants. So we will go through the entire water cycle in city, from tap to receiving waters by the applications. Before we do it, I would like to spend 30 seconds by introducing DHI to those who haven't heard about us yet. We are independent, private, global company, more than 55 years of history, headquarters in Denmark, but nowadays having the offices around the world, like almost 30 countries. And what do? We do specialized consulting enabled by our digital technologies. Maybe some of you have heard about our well-known brand, Mike Software. And this is part of our digital technology that enables us to do the top specialized consulting in very different water environments, coming from rivers through oceans and also cities, which we will be focusing today during our webinar. Speaking about the application of digital twins or digital technologies, digital twin is the buzzword of today, and many consultants, but also users and water utility managers, city planners are using these words. And there are very different understandings about what does it mean. And what is the real digital twin? Is it only the some sort of data acquisition systems with a little bit of machine learning techniques on top of it? Or is it something that includes also the deterministic models to forecast the future? Or is it complete digital replica of physical infrastructure, including the processes and systems and people working with? And the answer is, it's all of it. It depends about what kind of maturity the user would like to use, is able to use in terms of also reaching maturity of physical system, and what should be the focus of the digital representation, and what should be the task and the goal of that of the digital representation of the physical system. If it is going to be something to analyze, then we probably, let's say, use deterministic models with a bit of data around it and some dashboards to show about what if-then scenario is going to do. If this is the task to suggest what the operator should do in the next minute, then we are probably talking about a very complex and comprehensive prescriptive analysis and systems. And that's something how we define the stages of development of digital twin, from descriptive, kind of easy way to use and easy being implemented digital twins, through diagnostics and prediction to prescription kind of analysis. And these steps can be independent, can be following each other, and any kind of user of digital replica and digital systems can jump into that kind of path in any point. So if you already are using diagnostic tools, I mean mathematical modeling for if-then scenarios, then it's okay to jump into the implementation of digital twins in that moment and go farther on. Speaking about these stages, it also depends on what benefits you would like to get by using the digital twins. If you are looking into investigations of historical data sets, then probably diagnostic analytics will be okay for you. And as I mentioned already, if you are looking into making recommendations, how to achieve the best performance of your system, whether this is water distribution or wastewater treatment plant, then you are looking into full implementation of the digital twin. So what are the digital twins good for? Well, I already said that they are good for gaining the knowledge about how the physical system is working and support go, no-go decisions during system run and so forth. They are also very good for making tests and optimization, how these infrastructure should be working, optimization offline, so to know the scenarios and then to implement the scenarios in real life, or to run these scenarios or even suggestions for scenarios in real time and help the operator to optimize the system at that moment. So that used for testing and optimization to make systems compliant with their KPIs. KPIs like effluent standards for wastewater treatment plant, or reaching the number of the customers in water distribution system that are not actually without any delivery of water and so forth. Finally, and this is the right side of the slide, they are good to use for training of the staff. And when I say staff, it means the staff of the, for instance, water utility who are operating these systems, but also the stakeholders around, city planners, consultants. So they are all talking on the same level of information and at the same platform. To achieve all of these goals by digital twin, they must be fit for purpose. They must be built. They are fitting for purpose. So then means that they are co-created with those who are going to use them afterwards. Otherwise, the future use of these digital replica or digital twins is very difficult, because the people who are going to use them later, I mean the users, are not really engaged with the development process of those digital twins. To do it, it means that we offer, and this is our approach, to develop these systems step by step, and this is what we call kind of road to operating infrastructure as its best. And as I mentioned at the beginning, at the beginning of this introduction, today we would like to show you the 3 different examples from 3 different infrastructure pieces of urban water systems. Water distribution online, as I mentioned, that will be given by Peter, about application from Cape Town, Romana, Acre, and some other places. The application of future city flow as a second part of our webinar, given by Dennis, examples from city of Gothenburg and Trollhättan, and finally application of twin plant, which is our commercial name for digital twin of wastewater treatment plant, and that will be given by Henrik. So that was my introduction to the webinar. Thank you for joining. If you would have any questions, please write them down in the Q&A box of the webinar, and I will hand over straight to Peter Engelholt, who will start to showing you the digital twin application for water distribution networks. Peter, it's your time, and the floor is yours.
Well, thank you everyone for joining our webinar today. In this first demonstration, we will focus on water supply and water distribution. My name is Peter Ingerud, and I will take you through this demonstration. So there was a brief description of digital twins provided by Hunza, so I don't need to repeat these general characteristics. But I'd like to highlight one important aspect, and that is that digital twins, in order to be operational, they need to be continuously updated based on SCADA, based on telemetry, based on other data sources. So that is the main difference between standard classical model and model used in digital twin system. And so the backbone or the core of digital twins is online version of a hydraulic model. And that means that we have hydraulic model developed and calibrated to a certain degree, and that is schematized on the right-hand side of this picture. And then we have the actual system, and we need to develop a mapping, sensor mapping or data dictionary between the telemetry, between SCADA, source of the live data, and the hydraulic model. And so for every storage tank, for every pump, for every valve in the hydraulic model, we will find the corresponding SCADA element, SCADA tag, and develop the mapping. And the same goes for turnouts, for zone consumptions, or for the total network demands, things like that. And once we develop this mapping, the hydraulic model can start running automatically and periodically and be updated based on the telemetry. And so the architecture of digital twin is usually something like this, that we have a server with online model, which is connected to the source of SCADA data, whatever the source of SCADA data it is. We support different formats, including OPC. And then on the same server where we have the hydraulic model, we would be running data pre-processing and post-processing and analytics, hydraulic simulations and water quality simulations and demand predictions, whatever is required by the digital twin. And then we would provide some customized interface or web-based interface that will be used by the operators, by hydraulic engineering, by users of the digital twin. And we provide interfaces that work both on desktops, computers, and smartphones or mobile devices. This slide is from one of our actual implementations. This one is developed for Cape Town. So there is a certain degree of complexity into how different parts of the systems are distributed. And we also need to keep in mind that some parts of the system, especially those where the SCADA data is, are disconnected from internet, are protected by another level or layer of a firewall. And so it might be quite challenging in the end to put all this together and run it. The digital twins that we developed, they provide for 3 different operating modes. There is a real-time mode which runs in average, every 10 minutes. And every time it runs, the hydraulic model will be synchronized based on the telemetry data and other databases. And the simulation will run, and it will provide simulated data and compare what is measured with what is simulated, will generate alarms, things like that. And that is used to provide operational descriptions of the system, and whenever there is a need by operators or engineering to take the latest model and use it in their analysis, they use the real time. And then we have forecast mode, which will typically run several times per day, once per day, twice per day, or every 3 hours. And in the forecast mode, The hydraulic model will run prediction of hydraulic or water quality conditions for the next several hours or several days. We usually do up to 3-4 days. And then we provide for hindcast modeling or forensic modeling, which typically runs on a request. And in this mode, the model or the digital twin will be developed for certain past period. For instance, what happened yesterday at 8 o'clock in the morning, or to simulate Wednesday from the last week, etc. Now we have few illustrations. This is the interface that we use. So there will be, there is a map with the hydraulic model and either hydraulic results or telemetry points, as it is shown here. And then we have time series plots with simulated data, with SCADA data. And we have options to run different user scenarios, different simulations. And this whole interface can work very well on mobile phones or tablets. This picture shows part of the water distribution network. These green and red dots in the map, they show flow sensors and pressure sensors. And if the user would select the sensor and click the sensor, he would get time series plots. And there will be always couples of time series. One of them will be from the model simulated, and the other one will be from the telemetry, so that it can be used to visually compare simulated with observed. And then we have alarmings on the top of this. And here is an example of water quality simulation, contaminant spreading based on the real-time model. That brings us to what is a typical use of digital twins. So there might be different use cases. There is this virtual, the real-time mode or snapshot simulation, which is used to update the model and make the model ready for simulations and to compare simulated with observed data. And then we have alarming. Alarming can be used to generate alarms whenever we have differences more than a certain degree. And then we have forecast simulations, short-term predictions. We have hindcast simulations. We can do real-time simulation of water age. And this whole system can be also used as a training simulator, for instance, where either engineering or OMA department or the system operators can use it to simulate what-if scenarios. And of course, it serves this emergency response purpose. I selected several of our implementations. There is one which was developed in Zurich in Switzerland, and this one has been operational since 2016. What we do here, we develop hydraulic model and we update the model indeed, but the primary goal of this digital twin is to simulate water age in the real time, which was more difficult than we thought originally. But then after this was implemented, every time you look at the screen, you look at the outputs, you would see water age in hours in the system. And this water age is changing based on how the system is operated and based on what happens in terms of maintenance and availability in the system. So that was one of our first implementations. Then we developed this one recently in Toulon in France. It's used primarily for pump and valve scheduling, so that we develop the system to support operations, to support operators and help them to develop optimum plans for the next 4 days, how to operate their system. Because we need to do forecast simulations, we developed a demand forecast system for different turnouts and zones in the system based on machine learning. So we developed this forecast of water consumption, and then that is used in the hydraulic simulation. And this is output from the optimization model. It runs twice per day, and every time it runs for each pump station, it develops a plan how the pumps needs to be operated. So here we have Fortouche Bas pump station, and here we have Fortouche Hall pump station. And these pump stations, they have 3 pumps, and in these dots, they represent how many pumps are running at a certain point of time. This one was developed for Romagna Aqua system in Italy. It's a large regional water supply network. There's several hundreds of points where the data are exchanged between SCADA and the model. There are about 460 control valves, and each of them is receiving input from telemetry and is being changed in the hydraulic model. There are 54 pumps, 63 storage tanks. So this is almost 600 sensors that are used to update the model, and then we have others for comparison purposes. The system runs in the real-time mode. We do forecast, we do hindcast simulations. This one is being developed for Cape Town in South Africa. It's a part of decision support system to help to improve water supply conditions in Cape Town, optimize water resources and save water. Again, it's quite complex system. We have about 200 control valves, 16 storage tanks, 12 pumps, and all this runs in the real-time mode and in the forecast mode. And this is an illustration of differences that are generated whenever something happens in the physical system in the actuality, which is not accounted for in the hydraulic model. And this particular screen shows, you see very big disagreement between simulation and observations. And they were caused by the actual pipe rupture, pipe break of 300 mil pipeline. So when this happened, the pressure dropped, and we could see sudden difference between the model and between the observed data. Now I will play a little video. It's a short video which will illustrate how the system works, how the interface works. So here we have the hydraulic model, and when I recorded this video, I updated the model. So this, whenever you connect to the system, you would have the actual date and time when the model was updated for the last time based on telemetry. And then we can take a look at the map and take a look at comparisons, and then we can see, as it is here, whenever there is a green dot, the comparison was very good. When it was blue, it was like acceptable comparison. These comparisons are also archived, and we can develop alarms and take a look at the alarm scroll in time and see what happened and why. And then we can do time histories of observed data, pressures and water levels, and velocities. And for distribution zones in the system, we can select the zone, click the zone, and see the current consumption in liters per second or the flow units. And then we can take a look at the time history of water consumptions in that zone. And also, and that is illustrated here at the end of this time series, the actual data collected from telemetry, they end here. And this part of the time series, it's a product of demand forecasting, which is implemented here based on machine learning. So it predicts what would be the water consumption in the central zone. So this is part of the digital twin here as well. So this way you can navigate through the system and take a look at different parts and investigate the observed data and the differences between simulated and measured. And then you can take a look at the hydraulic results anywhere in the system based on the hydraulic simulations. And again, you can scroll in time and take a look at the pressures or gray line in the entire system and do mapping or display time series. So in this way, you can actually take a look at the detailed results of hydraulic simulations and scroll back in time based on the history that you decided to archive and see full hydraulic results in the map. And then finally, you can create your own scenario, and then you can run hydraulic simulation. You can do some changes to the system, or you can do fire flow simulations. You can simulate shutdown planning. So you have access to very complex analytical tools here. So that is the end of the video, and I will go back to the presentation. And there is the last slide with some conclusions. I decided to call it lessons learned and confirmed because we can see that some of this experience that we have here on the slide is repeating every time we develop the solution. So first, it is important to realize that the infrastructure of water distribution systems is never 100% known. So there is always some degree of uncertainty due to either unknown conditions of pipelines, but also due to pipe breaks and repairs and reconstructions, things which are going on. Not all operations are recorded or monitored. So there is, again, certain degree of operation, flushing or hydrant operations and isolating valve operations that happen in the actual system but are not recorded, not stored in telemetry. There are also very frequently data security issues related to no internet or separated networks with SCADA. So we provide cloud systems, but we need to provide them also on-premise. So this data security, this creates additional issues that might be time-consuming and bureaucratic. There might also be some data gaps in the SCADA data. The modeling team on both consulting and the client side need to include IT personnel, and that could also be challenging. And in our opinion, it's always very important to involve engineering department in this digital twin because they know probably best how to use it. And finally, the hydraulic model and this whole digital twin, once it is developed, it needs to be updated. Without regular update, it wouldn't live long. So this was the last slide. I thank you very much for your attention, and Dennis will now take over.
I hope you can all see now my first slide. And thank you, Peter, for taking us through the first part of our integrated urban water management chain. My name is Dennis Wanninger, and I will take you through the next part of our integrated urban water management chain, where the water moves from the tap and into our collection system. Where on the distribution side you are concerned with water leaking out of the pipes, I'm mostly concerned with excess water leaking into the pipes, causing flooding, overflows, and bypass of partially treated water at the treatment plants. In essence, we all share the same challenge, whether we live in Sweden, Canada, or Australia. And our objective is to ensure that all urban water remains in our green infrastructure, our pipes, and our treatment plants. I think it's safe to say that we are experiencing our treatment processes being disrupted. The causes of this disruption mainly comes from climate changes, population densification, and aging infrastructure. And as a response, we wanted to develop an easy-to-use solution that would effectively reduce the overflows, the flooding, and the discharge of the partially treated water at the treatment plants. There's no doubt that the challenge we have in front of us is complex. Most of us are familiar with the most common consequences of dealing with inflow and infiltration, such as the overflows and flooding and the bypass. However, many of us lack the methodology, the governance, or the insight to execute effective strategies, and we are ill-equipped at demonstrating the effects of carried out measures. And with regulations tightening, it's no longer a question of if you have to comply, it's a question of when and at what cost. With that in mind, we at DHI took our domain knowledge and our digital expertise and developed Future City Flow. Basically, Future City Flow uses a model of the collection system, it connects it with various data sources, and it presents it in a graphical user interface for result processing and analysis. But obviously, it's a whole lot more. We also use weather forecasting, we use real-time sensor and gauge data, and we use a hydrological and hydraulic model to predict inflows and loads to the collection system. This is then integrated in 2 operational cycles. By combining model information from the collection system with site-specific level and flow variations, you can leverage real-time forecast to execute weather-adapted and model-based control strategies and prepare your infrastructure for expected flow increases. Further, you can also put an end to spending time and money on ineffective and reactive measures by predicting both the long-term and the short-term impacts of potential infrastructure improvements and return on the investments. For today's webinar, I would like to share 2 examples of Future City Flow implementations. I will use the case of Gryap, who is the owner and operator of the treatment plant for the city of Gothenburg and the surrounding municipalities to demonstrate the real-time control application. And then I will go to the city of Trollhättan to demonstrate the planning application. The Rya wastewater treatment plant is operated by Gryap and is located in Gothenburg, Sweden. Gothenburg is Sweden's 2nd largest city, and it treats wastewater from Gothenburg and surrounding municipalities and has about 900,000 PEs connected to the plant. Their collection system consists mostly of surface sewer system and a tunnel network that leads to the treatment plant. About 40% of the sewers connected are combined, which results in variations of up to 7 times in hydraulic loading to the plant. Further, the plant is only manned part-time, and outside of regular work hours, standby crews can securely monitor and adjust plant performance remotely from their homes. The overall objective of implementing Future City Flow was to manage issues related to sewer overflows and to reduce storm weather impacts on the treatment plant by leveraging the tunnel storage capacity to a higher degree without having to increase capacity at their current plant, or even in a worst case scenario, building a whole new treatment plant to fulfill new regulation permits. To achieve this, the process or approach was that we implemented an operational digital twin with online flow predictions and suggestions for control strategies. So the aim for the digital twin was to allow for increased confidence in decision making, as the effects of a change in control strategy could be visualized quickly. And to determine the recommended control strategy, Future City Flow uses an algorithm to optimize the pumping scheme to achieve inflow to the treatment plant that is as constant as possible during the coming 12 hours, while still considering boundary conditions such as allowable water levels in the sewer, pumping capacity, and pumping conditions. Simulations performed at the beginning of the implementation indicated that the discharge of untreated wastewater could be reduced by as much as, I think, 50% in the Gothenburg case. Here, I just wanted to show you a picture, a snapshot taken from the control room at the treatment plant. So what you see here is 2 operators, a lot of monitors, and Future City Flow on one of the 2 main monitors on the right-hand side. So Future City Flow runs 24/7. So even when operators are not on site, they can access the data securely to obtain updated forecasts on expected loads. So one of the screens that I have taken out here and to show you is one that the operators can see from the system, and it's a visual map of the operational area. So the red lines that you see here represents a schematic overview of the tunnel system that runs in the city of Gothenburg. In addition, you also see a number of different critical points in the network and the collection system, and they can be overflow points, they can be level or flow meters, rain gauges, and obviously the treatment plant in itself. The colors at the different points indicate how the infrastructure is doing and what is expected. So green indicates that all systems are running below the threshold set for each point. Yellow indicates that there has been an event at that point, and red indicates that the system expects an event which will result in an overflow or increased inflow at the treatment plant in the coming hours or days. So on this screen here, the operator can get a fast overview and be notified about any upcoming events that may result in increased flows and levels. The next screen I've chosen to show is the actual control part of the application. Based on expected precipitation from the weather forecast, Future City Flow simulates different outcomes and can suggest a controlled strategy that removes uncertainty and ensures that the infrastructure is prepared for the coming load. Kind of what Peter also explained earlier, to avoid discrepancies between current measured values of flows and water levels, both in the sewer network and in pumping stations, and the corresponding values in the hydraulic model, Future City Flow uses data assimilation techniques before each simulation, and we can adjust the forecast according to identified patterns of deviations before and between measured and simulated values. So with the rain that we saw on the previous screen here, coming in here, you see a rasterized picture here, we can see the expected flow if you do not use the system control strategies that are suggested by Future City Flow, and that's the line that we have here. Below here, you can see the expected flow is if using the system control strategies. So based on the weather forecast, Future City Flow expects an inflow that is higher than what the treatment plant can handle without emitting partially treated water, which starts here at 7 cubic meters per second. So we suggest initiating both of the two available pumps on the inlet in order to empty the tunnel before the rain hits the system. And that's what we see happening here. The pump starts and the flows will go. We empty the tunnel and we can keep the flows into the treatment plant below this threshold here. And we actually manage, by using this control strategy, to keep a very good margin up to the first critical discharge point. So for GRYAP, by combining data from their sensors and gauges, the weather forecast, and the hydrological and hydraulic model, GRYAP was able to optimize their operational control strategies and use their existing infrastructure in a more efficient way. The outcome was that they were able to postpone a very significant investment, and they were able to comply with the regulatory targets. They achieved a more steady inflow to the treatment plant, which leads to a more stable treatment process in general. And they experienced lower risk of reaching those critical load situations by pumping water from the tunnel system before large flows are expected, and thereby avoiding large flow peaks that can be hard to handle. If we move over to Trollhättan, it's a different story. So in 2017, the city of Trollhättan received regulatory requirements that the share of inflow and infiltration in the municipality as a whole could not exceed 60% by 2013, and that's where they were currently at 70%. Without being able to visualize the effects of carried out measures from the last 10 years, the city of Trollhättan were not able to counter the regulatory requirements. So Future City Flow was implemented to visualize and communicate the effects of their carried out measures, and also to identify target values for the coming 10 years plan and how these could be realized in the best way within reasonable time and at the lowest investment. What Trollhättan did was to enter all carried out measures from the last 10 years in order to visualize the achieved effects. The insight gained from that exercise gave Trollhättan the ability to compare different catchments with respect to how they contribute to inflow and infiltration and how much overflow is generated in the specific catchment. Trollhättan then used future city flow analysis to recommend focus measures for the coming 10 years. A snapshot of those scenarios is what you see here on this screen here. And as you can see, one of the scenarios here yields an almost 16% reduction in overall inflow and infiltration, with a cost not much higher than many of the other scenarios. The next task was to take all of these scenarios and put them into a realistic execution plan for the coming 10 years when taking budget and effects into account. Future City Flow, together with Trollhättan, simulated hundreds of different scenarios with the aim of identifying and visualizing the optimal combination of both measures within budget, time, and target effects. The optimal combination was then used to suggest to the user, allowing the users to see the effects, cost, and planning for the coming 10 years. The user can then decide to go with the suggested plan or change the conditions to accommodate other priorities. They can even do that on the fly while discussing the plan with, for example, the regulators. The city of Trollhättan was able to create a well-documented review of the effects and cost of their carry-out measures, as well as a realistic plan for the coming 10 years with regards to achievable outcomes and budgets. This was communicated to the regulators and resulted in the review of the regulatory requirements set back in 2017, with the approval of new regulatory requirements being the end goal. So for the city of Trollhättan, implementing Future City Flow resulted in, first, a better insight into what catchments contributes the most to the problems here and now, but also in the future. And it also provided them a visual platform for comparing different measures. We strongly believe that by embracing digital twin technology and combining data sources, you can ensure greater confidence in decision-making and optimize your current conditions without making big capital investments. And that's the essence of why we, first of all, developed Future City Flow. One of the prerequisites was that you have to go in and think that we do not need to add more infrastructure. We need to work with the current infrastructure and optimize it in a way where we can utilize storage capacity in a better way so that we do not have to invest. And with that said from me, I think I will hand it over to Henrik, who will take us through the final part of the water cycle, namely what goes on inside the walls of the treatment plant.
And my name is Henrik Sørensen, and I will, as Dennis said, kick the water, the last part from the collection system, into the treatment plant, where we have a solution that we call Twin Plant, which can help us. And Twin Plant is essentially a framework that allows you to do automated control and establish digital twins for wastewater treatment plants. And there's no doubt that that automated control and digital twins can help you a lot in reducing your operational costs, and also sometimes or quite often reduce capital investments, as Dennis just talked about. And it can also help you in becoming more efficient in terms of cleaning your water and spending less energy and so on. But I would also say that if you have aspirations that goes beyond compliance, maybe you are looking into livable cities and you go beyond compliance to meet some of the, or to contribute to some of the sustainable development goals, then I think that that's very hard to imagine that you can do that without some kind of automated control and digital twins. And the photo here shows people swimming in the harbor in the city of Aarhus here in Denmark. They are surrounded by recreational areas and expensive housing, and all of that, of course, requires clean water. And there's no doubt that for the city of Aarhus, the water wouldn't be clean unless they had a well-controlled collection system and treatment plant in place. So I think that's a good example of what you can do with digital twins. But if we move a bit deeper into different types of performance goals, then of course you can talk about livable cities and compliance and sustainable development goals. But the 6 that we see here are probably the most typical goals that you want to work with when you construct twin plant solutions. So that's about process efficiency in terms of cleaning, how well you clean your water. Resource efficiency could be in terms of how much chemicals you use, but also how many resources you're able to recover. Cost efficiency is always important. You can get an OPEX calculation for your entire treatment plant operation. Plant capacity can create large savings because it can postpone, at least push major capital investments in infrastructure. So if you are in need of capacity, that's often a big gain. Energy efficiency is very typical, and also carbon footprint, greenhouse gas emissions. So those are probably the most typical goals that you want to work with when you do a twin plant implementation. The concept twin plant covers a bit more than what you would normally call a typical digital twin. We have these four, you can say, steps here that we call the automated plant, the learning plant, the predictive plant, and the optimized plant. And twin plant covers all of them. And if we dig a little bit deeper into them, then if you look at the physical system, you would have a number of sensors installed that would deliver different types of real-time data from the plant. It could be dissolved oxygen, ammonia, nitrate, and so on. And they would go into what we call the automated plant. And what the automated plant essentially does is that it calculates set points, which could be set points for pumps or blowers or chemical dosings or whatever. And they calculate them in more or less sophisticated ways, but it's basically just a function of this real-time data that gets in. These set points are transferred back into the physical system through the SCADA system. And as you progress to the learning plant, the predictive plant, and the optimized plant, it is essentially about improving the way you calculate these set points so that you better meet your KPIs. And if you take the first step, then we start to move into what we would normally call a digital twin, where we have a real-time online process model in place. And what you can do with that process model, which we do very often, is that we use the model to help continuously improving the way that these set points are calculated. So we are fine-tuning you can say, initial set points using the model. There's typically a lot of value included in that. And the next step you can take is that you can add different types of forecast products. So inflow and load forecasting is an obvious one. And if you do that, then you can start to look 3, 6, 12 hours ahead. And that gives the operators the tool to try to improve the operation of the plant on a short time horizon. That's also used quite a lot. And the last one is then where you can say now it's a fully automated, optimized plant where everything runs in a completely automated manner, optimizing the set points in real time and pushing them back into the system. And in principle, that can be a robot, but it's probably more realistic that it will be some kind of human augmentation where we can propose optimized set points, but that there's still a sanity check by a human before they are pushed into the physical system. We actually don't really know how far we can get with that yet, but we're starting to work on what we call the optimized plant in a few occasions. But that's basically the twin plant concept or framework. And when we build digital twins for treatment plants, they would typically look like this in terms of functionality. You have connections to your sensor data. You get real-time data from the plant. We have a system called DIMS Core that can connect to SCADA systems and does do a quality assurance, data validation, and data processing, but it doesn't have to be present. But that's typically the way we do it. Then we would push it out into the cloud, could be Azure, where we would execute a process simulator that calculates set points. We would have a web-based simple user interface that the operators can use. And all of that would be scheduled on an automated workflow, for instance, on an hourly basis. So that's typically the outline of a digital twin, which would then be used by operators or process engineers. If we look into a few cases, then I think the whole story around Aarhus, the second largest city here in Denmark, is pretty good because they have a very strong vision and a very ambitious vision about building the world's most resource-efficient wastewater treatment plant. They call that Aarhus Rewater, and that's the plan to have that established by 2028. So in about 7, 8 years from now, and that actually will require that they consolidate these 3 plants, Åby, Viby, and Marselisborg, wastewater treatment plants into one new plant, which will also be located here in the harbor, which is then the Aarhus Rewater plant. And they will still keep AO treatment plants. So they are consolidating the 4 plants into 2 plants. And we are working on EO, which is then one of the plants that will survive. We are actually building a digital twin here, which is progressing towards including all the packages, also including the optimized plant. But today it does the automated plant, the learning plant, and the predictive plant. And we're starting to work with optimization of the set points now. And the user interface here is the one that we typically deliver with digital twins. It's supposed to be simple, to give a quick overview, including an overview of how well your plant performs on the APIs. It gives you alerts if anything is not as it should be. It allows you to click on any of the objects here and drill down into data. It could be real-time sensor data, it could be the model data. It gives you access to inflow forecasts, which you can then use for your operation. And it also, in the same context here, allows you to create scenarios where you can then try to see what can we do to improve the operations for the next 6, 12, or 24 hours, for instance, just the next example. So that's underway, and there is a digital twin running. We are working on the optimized plant. If we look at VB as another example where we are then using the automated plant and the learning plant. The VB is one of the plants that will be decommissioned in about 8 years from now. And when we did this in 2018, the expected lifetime was then about 10 years. But the Aarhus Water knew that they would have to increase the capacity by about 33%. And of course, they weren't super happy about spending a lot of money on expensive infrastructure on that plant, since it had a relatively limited lifetime. So they asked us to see what we could do with the automated control here. And we actually managed with the automated plant and the learning plant to increase the capacity to the required 120,000 PE, so that the plant can survive for the next 10 years until rewater is ready. And that was done for around 2 million euros, which in this context is cheap. The alternative, which would have been investing in more infrastructure, would probably have been 10 to 15 times higher. So we created a short-term, cheap solution for Aarhus Water here by the automated plant and the learning plant. Aarhus Rewater, which is then the new plant, is super ambitious. That's where they said we want to build the world's most resource-efficient wastewater treatment plant, and of course that will include all the elements of twin plant, also including the optimization, and they will also be focusing on all of these KPIs that we are typically working with. There will also be more. There will be something about health for sure, and there is also a very close connection between these KPIs and the Sustainable Development Goals. The Sustainable Development Goals is a very important part of Aarhus Rewater's vision. So that's going to be super interesting, and it's not a project that we have yet that has been committed to DSI. Aarhus Rewater is right now evaluating different possibilities here, and of course DSI hope that we will be the selected consultant here, but we don't know yet. So it's not something that we're doing yet, but it's a very interesting project no matter what happens. We have done a number of implementations around the world, and this is not all of them, but just an overview of some of the smaller implementations and some of the bigger ones. And it shows, I think, that almost all treatment plants has a focus on process efficiency, which is of course important. They want to comply with the standards, and they want to clean the water as best possible. And cost is also always important. And then you can see that energy is typically important. Plant capacity, like we talked about for VB, is also sometimes important. But then you can see the bigger implementations like Aarhus Rewater, where there are high aspirations, and also LA County, they tend to focus on resource recovery and carbon footprint, and also the Sustainable Development Goals. Yep. In the works, I would say compared to Future City Flow, Twin Plant is still a little bit less mature. We are still working on a number of things that will make it turn it into a mature solution. Some of the things we are doing here is working with anomaly detection using machine learning. We are working on a better real-time automated calibration process, so we can improve the predictive capabilities of the models. We are working with different types of inflow forecasting, also looking into how we can use machine learning to convert radar data into flows, for instance. but also looking into how can we actually do a better process model forecast. So how can we better forecast the processes that happens in the plant? And then also we are working with the different types of optimization approaches. And again, here I think it's going to be interesting to see how far we can get with that. I would say that the first three, the automated, the learning, and the predictive plants are mature, quite mature, while the optimized plant here is still where we have a good deal of things to learn. Thanks a lot for listening in. That was all I had here.
Thank you all, gentlemen, for your presentation. I would like to thank you for joining us today. Hope you enjoyed the webinar and hopefully see you in some other DHI event. Have a nice day.